Good morning, you guys. You able to hear me?
Yeah, we can hear you.
Okay, great. No echoes, right? No issues. Okay, great. Thanks. I can hear you clearly as well. So we can get going whenever you're ready.
Okay, we have shared you the document. Well, no, we're sharing on the screen right now, on that screen. Oh.
Yeah, I can see your screen. Maybe you can click on home so that all the tools are hidden. Yeah, great.
Use the mouse. Yeah. Like below.
Yeah, that's good. I can see that.
And then like maybe zoom in.
Is that good?
Yeah.
And then we just scroll.
Can you see us?
I can see three of you. I can see just three of you. I can't see probably.
How about now? Are we good now?
Yeah, I can see all four of you. Yeah.
All right, so let's just start off simple with the loads. There's different types of forces. I think the first thing that we thought of was forces. So friction, centrifugal, gravitational, electromagnetic. When we first start out loading forces, something like this is common, where you see box in a rim and forces in different directions. So just wanted to show how different forces work together and can be used and can't. And then down here we have point load and distributed load. This is used pretty often in structural analysis. A lot of things that basic concepts.
And so when we talk about forces, we want to translate it specifically to stresses that are on our structure. And so we're using, as we mentioned in class actually, the law of reciprocity is cut off here. Well, it's also known as Newton's third law. We're saying force is going to be equal to stress in the same direction times the area that it's being applied on. And in this case, we're using 1-1. This is a general description, but it's in this case it would be where 1 is the longitudinal direction and x2 in the transverse direction. So you'll see they're acting in the same direction. And then next up, if we're talking about stress, it's important to have like some kind of like sign convention set up. And so we have a really good diagram that describes the general setup of how stress is described, where if you have normal stress, which is acting directly on pointing towards or perpendicular to the surface, it will be normal stress. Whereas if it's going along the surface, we're calling that shear stress. And then when we're talking about normal stress, we always have separated into tension and compression. If it's like pulling it out or pushing in on the structure. And if you get to constitutive law, we'll go in more depth about this, but we're going to talk mostly specifically about like the different modulus that we have. So I think I can zoom in better onto this diagram. And you can see like the different modulus we have when we talk about elastic modulus or Young's modulus, where it's basically based on axial loading. We have the shear modulus, where we're focusing more on shearing. Bulk modulus, we'll talk about later, where we talk about more about like pressure. I feel like a submarine example for that. And fluctuating modulus, we have it on the diagram, but we didn't really include it in the slides. And in this case, we have, you can see that it assumes much of the assumptions that we made in class, where it's elastic, the relationship is linear, and that's how necessarily we would get with a slope is how you get the Young's modulus. But we'll see later on that that's not necessarily the case. There's a less assumption that we can make and more precise version that we can use. And going along with the definitions, we also have the definition of strain, where it's a change in length of the original length. And we also have,
That's really just a really basic equation. We'll go more in depth on that for sure. So this is the stress versus strain.
I lost your audio. Are you able to hear me?
Yeah.
Yeah. Just for a few seconds, I lost your audio. Yeah, go ahead.
You want me to start at this?
Yes, you can start from the strain. I think I heard it till the strain. Yeah.
Oh, okay, so we just talked about this briefly. It's just a change in length over length. We will go into much more detail with this. This is just a very simple, equation. There are more complicated equations. Now let's talk about the stress versus strain graph. The reason we put it over here is because of the point of fracture. I think it really suits that it goes from the amount of strain to the point of fracture for a beam or for any structure. In this, there's multiple points to point out. The yield strength, the ultimate tensile strength is really important. We start out with this elongation period here, strain hardening, and then we have necking, which we've done a lot of experimentation in, like 2610 or 3610, where a dog bone shaped beam experiences necking, and then fracture, which is the point where the plastic deformation or the plastic region ends, and then it cracks, right? So, and then that's.
okay, and the whole point of that was to talk about how it leads to deformation, where we always say the elastic region, we can reverse the whatever change in loading condition, or what we can reverse the conditions that we applied and still return to like a reasonably usable structure. Whereas really you reach to the elastic region where we have plastic deformation, and it can also lead to points of weaknesses in the structure.
Just one suggestion, if you go back to the deformations. Yeah, you go up. Yeah, so I understand what you exactly mean when you say fatigue, buckling, creep, all cause deformations. But remember that these are a little more broader topics. So I want you to be a little more specific when you say buckling, for example, the buckling deformation, right? Because there can be buckling load also. There can be buckling as a phenomena also.
These are just general examples of deformation that we put at the top. So then later down in the presentation, we'll talk more about examples of the equations for bending mode.
Okay.
We get really specific into some of these concepts. Not
Sure,
maybe specifically, but these are just examples. We get pretty deep into other concepts. So it's not,
okay, and the reason I'm saying is because it's listed under deformation. So so when you say you list it under deformation as not as a concept, right? So you list it as the deformation due to fatigue or the buckling deformation or the creep deformation, right? Similarly, the stress strain curve, why is it coming under kinematics?
Because we're relating it directly between points of strain and stress to where deformation occurs. Like that was the main idea, where we're identifying points on the graph, and we're saying that if we go past this point on the graph, it'll lead to some sort of deformation.
even though the deformation is happening throughout the entire graph.
Yeah.
We felt like it would, suit our narrative.
Yeah, but as you see, the name itself is stress strain curve, right? So which is
Of course,
relating
yeah.
the stress to the strain, which means that it should come under the constitutive law, right? Not under kinematics.
All right.
Whereas kinematics involves strain deformation relationship. So what you listed as epsilon naught, for example, should go under the kinematics column. That is your G column.
This should go under kinematics. Okay. All right. All right.
You see my point, right? So you see why I'm saying that?
Yes. Yeah. Yes.
Yeah. Okay.
We'll have a change button.
So I'm just pointing out two examples, but this is kind of valid for a lot of other things that you're doing as well. So just make note that whatever is listed under a particular column is of the kind that the header of the column is talking about.
These equations right here translate between normal and shear stress. So I feel like this box are related in that sense. And you know, it's just basically translating between normal and shear stress. The equation's kind of cut off here, but this is something we learned in informal bodies, right? So.
Mm-hmm. Yeah, and also make sure that you adjust the column width either automatically or manually so that nothing is cut off. Like, for example, that constitutive law, the stress is being cut off, right? In column D, you could probably increase the width a little bit.
We did the entire thing in Google Sheets and we just downloaded it and converted it into Excel. And so that's why.
No, the equation seems to be fine, just that the column width of D should be increased so that you can see the stresses as well. The last column.
Yeah,
Yeah, you understand what I'm saying?
I can show you the Google Sheets. I think that
it might be just open the Google. Because that just first here.
Ah, okay.
It's in the.
you see it's
and
better.
So it fits in.
Yeah.
Oh yeah, okay. Yeah, now it's fine. Yeah.
Scroll down.
Yeah. So now we have two 6x6 matrices that relate stresses and strains, with one of them, this one below, that we derived in class, and this one we found from the deformable bodies, which also relates to stresses and strains, but it also makes one of those assumptions that you told is not a good assumption, which was like in-plane stress, which is not good for composites. But I think in deformable bodies, we were doing just single material, not a composite. So that assumption was a bit more reasonable. I would assume that's why that matrix is used. And then, yeah, we finalized the matrix from class just to fit in, and it does relate to the stress and strains well for composites. And yeah, so we done all the equations. And then we're going to talk about the derivation of the C44, which is the shear modulus in the transverse system.
Yeah.
So just the one note is then that this later on at the very end, we tied this into how this helps us to derive the C.
So to the right, we have the Solon's ratio, which we of course use in the constitutive law. We're displaying strain to strain. This equation is it's not necessarily the correct equation, but it always used to include the diagram. We're showing how causing a strain in one direction, where this is like the x1 direction, will cause a negative strain, whereas straining inwards the transverse direction. That's why the equation ends up being lateral strain and longitudinal strain. This should have been a negative sign, that the directions are opposite. The next step we're showing is the general equation for converting strain into actual deformation, or specifically displacement in this case, where if you're going in the x direction.
One more thing I would suggest for your final presentation is to actually name in the Excel these columns E, F, etc. With whatever the actual title is. So you can do that in Excel instead of calling them as D, E, F, etc., which is the default. You can actually give the name for each one of them. So it's not just so when you go down the slide, down the file, you can still see the headings.
This basically just relates the strain that's being caused or forced into creating whatever displacement is. We're taking the derivative, for example, like this is the x direction, or x1 direction. We're just taking the displacement, the derivative of u over the dx. And the same thing applies for the y direction and the z direction outwards.
Yeah, but truly speaking, even though the Poisson's ratio is defined in terms of the ratio of the strains, it is for a applied stress and it's a material property, right? So like all other material properties in the constitutive law, it also comes under the constitutive law. So it's just one of the parameters defined in the constitutive law. So it would rather go under an equation which is meant for the constitutive law. Which is relating the stress to the strain, because you're applying the stress in the one direction, because of which sigma gamma 11 is caused, and in turn also gamma 22 is caused, and you're looking at the ratio of that, which is a purely material property, and all purely material properties come under the constitutive law. Can you hear me? I lost your audio.
Yeah, we're
Yeah.
gonna fix the later ones.
Okay.
I can do it. So of course, we're applying a load or a force. It can cause a moment if it's acting at a displacement from where we're taking from the origin. And so that causes a moment. This moment will lead to can actually lead to a stress. We're going to show in this diagram. Basically, what we're showing here is the idea that
if you look at column A, row number 14, the beam that you have shown, with a moment at the support. So you can't apply a moment at the support, right? So either you remove the support or you show the moment. You can't show both, because at the support, you can't apply a moment. It doesn't make sense. You have to apply the moment at the tip or somewhere else along the length of the beam, and the support resists that moment. So if you're showing the reaction of the support, then you should not show the support itself. It becomes a free body diagram. So you can't show both the hashed and the circular arrowed quantity together. You see what I'm saying? Same thing with so same thing with the simply supported beam in column B as well. You can either show the reactions or you can show the support. You can't show both simultaneously.
Maybe what we're showing is that just the relationship between applied force, shear force, and moment, and how they're all basically the integrals of each other. And so you can start off with just an applied load. You can translate that all the way down to a moment. This is going to be a bending moment, where it can also be applied, translated into stress using the equation we have below, where IISc is the second moment of area in this case.
Okay.
And we mentioned that you can translate this bending moment into deformation, bending because it's a bending moment. But in order to do that, you have to include boundary conditions based on whatever support we're using or whatever fixture we're using. So in this case, we're using simply supported instead of pin. I have this small little chart here that basically just describes what these boundary conditions would be applicable based on what the support is. So if it's a free end, you have zero shear force with zero bending moment at that location. If it was pin, you'd have zero bending moment, as you mentioned with I think this diagram, zero displacement, as well as if it's fixed, you're gonna have zero displacement and zero slope, which is just gonna be like the derivative of the change in displacement.
So I just wanted to mention like how we can go from forces to shear to moment, right? So like that relationship is clear in this graph.
So once again, if you look at D15, you're talking of boundary conditions, right? So that's you put it under constitutive law. So boundary conditions are not under D is constitutive law, right? So you can't put boundary conditions under constitutive law. There are two types of boundary condition. Either you put let's say a fixed support or a hinge then you're essentially defining, for example, that the displacement has to be 0. So that's essentially a boundary condition in terms of the geometry. So that comes under kinematics. Whereas you can have boundary conditions in terms of the load, where you're applying the load. For example, in cantilever at the free end, you're applying, let's say, a load. So that becomes a boundary condition, which is part of the equilibrium equations. So you split the boundary conditions into two. So they will appear under columns which are meant for the equilibrium equations, which are called natural boundary conditions, and those which are meant for the geometry, which come under kinematics, they are called the geometric boundary conditions.
Okay, yeah, that makes sense.
Okay.
Continuing on, we have, as we mentioned, the equations, but we were just saying that taking the integral through each of these will lead you to the other ones. And also, this nice graphic that just explains how exactly bending deformation occurs, or how we derive these equations. Where if I zoom in a little bit more, let's go up here. So we're defining, it's obviously a beam, and we're bending it, where rho here is going to be our radius of curvature. Phi is the change in angle from where we bent it. And theta is going to be our change in displacement. It's our slope that would occur between the rise of the beam versus the original location where it was occurring. And so plugging these into the general equation for what a strain is, what we said was the change in length or the original length, we can see that strain caused by this bending moment can be directly related to the bending formation that occurs. And those are the equations that are to the right.
Lost your audio
so
again? Oh, yeah. Okay. Go ahead. I can hear you.
Can I go? Okay. All right. So for loads, I mean, one thing that we should really cover is aerodynamics. We're all aerospace engineers here. So, coefficients of lift and drag, how they're applied on an airfoil, right? Those are all loads that are being applied when an airfoil is in flight, right? Thrust and weight are also being applied when an airplane is moving. So, this is the very basics of how an airplane moves, right? So, and the very basic forces that are being applied when you look at the entire body as a whole. So, how do we relate that to equilibrium equations? We would look at Bernoulli's principle, for example. We can see that over a wing, low velocity but high pressure, high velocity but low pressure, right? And how does that relationship cause that lift to occur? So we go down right here, we have this equilibrium equation that basically shows both sides and compares both sides. They're set in equilibrium. That's why it's called. So it's a constant. So, the best way to relate that to stress would be pressure, right? Because pressure is force over area as well. So, in this example, we're using pressure. You can also relate pressure here as well.
We got a little thing to talk about deformation here. We're talking specifically about cracks and fracture and how it occurs. So one thing with cracks is that fractures, it often occurs with notches. But the thing is, in order to quantify that, it's hard to quantify exactly crack propagation. This is what I came up with in my MSc in the materials class last semester, where the critical stress intensity, which is basically the material property in this case, is directly related to the stress applied and times the square root of pi and c, where c is the length of the crack. So using this to directly predict, I guess, what critical stress or material property you need in order to avoid any significant failure to the structure you're using. And below we have talking about fiber diameter defects.
So this is a graph we discussed in class extensively. We're talking about fiber diameter, the tensile strength, and that curve that occurs. Now, this is not what would occur, if we were talking in the most ideal setting. But as we increase higher diameter, more chances for cracks to occur during the manufacturing process. So that's a real world. This is a real world graph compared to what would happen ideally. And when those cracks do occur, there's a higher chance for to fail, right? Basically, because there's a higher diameter.
Okay.
Are you there? I lost you again. Your video is frozen and I can't hear your audio.
Is it better now?
Yeah, I can hear you clearly. Yeah, go ahead.
So now we're going to talk about hydrostatic forces, which occur in compressible fluids primarily. So one example is a submarine in water is attacked by pressure of water from all directions. And we can relate those hydrostatic forces to pressure by the equation of forces, pressure times area. And some other equations that relate the pressure, basically equations for pressure. We have the group stress, longitudinal stress, which is true for thin-walled structures, like monocoque structures. So we have difference in pressures times the radius divided by thickness, and we can get the stress on that. And with that, we also can find the hydrostatic force. Then we can relate pressure to volumetric strain using the bulk modulus and difference in pressures. So difference in pressures is bulk modulus multiplied by volumetric strain being negative. So if the volumetric strain is negative, we have a contraction. So then we can relate the volumetric strain to the deformation through the change in volume. We assume there's a uniform change in volume as all the pressure from all directions is very similar. It will be the change in volume divided by the initial volume will give us the volumetric strain. And so the change in volume is a uniform contraction from all directions or is a uniform expansion from all directions.
This is, more of a system dynamics problem here, but I think it also applies. We're talking about forces with loads, damping force, spring force, and you can see that in the diagram here, and how all of that works together, right? And we can also write an equilibrium equation to relate, force extending here, the force of the spring, and the force of the damp, right? So that would be a way to turn this into an equilibrium, right? So we go from force to equilibrium. And that occurs because of the deformation of the spring and the damper, right? So we can also relate this to deformation because it's literally deforming the spring or literally deforming the damper.
So now we're going to talk about torque. Torque is very similar to moment in a way. So we can relate torque to shear stress by the following equation, where we have torque times the distance from the point of torque divided by the second moment of inertia, or the moment of inertia.
No,
Which,
no. Yeah, it's as I discussed in the previous class, J is not moment of inertia or the polar moment of inertia in general.
the
It
second
is called
moment.
the torsion. It's called the torsional constant. So it happens to be the polar moment of inertia for circular cross sections, both solid and hollow, but for no other cross sections. Okay, so always call it as torsional constant. That is
Yeah.
the more general term for it, and it will take on different forms depending upon the type of cross section.
Cross-section. Because for thin walled as well, very specific.
So you can change that polar moment of inertia, whatever you're written there. That's not right. Yeah.
Yeah. So we get shear stress based on torsion. Then we can use the shear modulus equation to go from shear stress to shear strain. So shear stress is the shear modulus multiplied by shear strain.
Yeah, I would like you to be a little more specific in terms of the tau, G, gamma, etc. With subscripts for the final presentation tomorrow. Because remember, there are three different shear stresses, three different shear strains, and different Gs as well. So just put appropriate subscripts over there to show what you're talking about. And this holds for all the other stresses and strains throughout this sheet as well.
And so also we know that the shear strain is generally an angle of twist or a difference in.
So similarly for the angle of twist, it's a part of a vector. So you typically put a single subscript. So in this case, it's θ1 because it is about the length, and we usually introduce the x1 coordinate along the length. So it's tan θ1 that you're talking about over here. And your gamma is, of course, on the one phase in the theta direction. So it will be gamma subscript 1 theta.
Yeah, so it leads to torsion. So one example is applied in the shafts.
So you see that in this figure you have used phi for the angle, so that theta should be phi, not theta. So you don't mix up the variables because you have in the polar coordinate system r theta z there. So theta becomes an independent variable, whereas phi is a dependent variable. So phi depends on x1. And so you have to make sure that the gamma subscript is 1 theta, but what is within the tangent is phi 1.
So it's like for thin walled shafts and torsion. So we will have a different J because it's thin walled, and so it's a different cross-section area. And then we have the final equation, which basically relates the deformation to the loads being the torque. And this will be the final equation you can use to go from one end to the other.
So as we're talking about geometries, we know it affects different constants, as we mentioned, the second moment of inertia, as well as the torsional constant, which we just mentioned. There are different ways of calculating that. This is specifically for, I believe.
So all these geometry aspects will come under column F, not under A and B, because there's something to deal with the geometry, right? All the lengths, the cross-sectional dimensions, the shapes, all of this comes under column F, if I remember right. Yeah, so it's the 7th column essentially. Sorry, 6th column that you should have it in. So it will be convenient if, as I said, if you, instead of calling it ABC, if you have that the title change, so that as you go down the sheet, we can continue to follow which column you're under.
I think we'll definitely do that. And so the way that we did this is before, this is a cylindrical example where the torsional constant is based off the perpendicular axis theorem, as well as we also included other theorems that are related to that, such as the parallel axis theorem. This basically applies for I-beams, where you're calculating, I believe it's the signal area. If they include that, this is the reason why I-beams would be superior in some sense than a normal just solid block, as it can prove a higher inertia by including the MD squared term.
Right. You might recollect that you would have studied some of these things as part of your AE2220 dynamics course as well, under a topic called kinematics. So, which is why all of this should go under kinematics, which is the second last column.
Yeah, so we're going to move all these different equations to the kinematics equation, the kinematics column. As we mentioned, the signal of inertia is going to be the integral of y squared dA. And that might be it for this.
I think one thing that we could really carry on throughout, most of this is true versus engineering stress, or true versus engineering just in general, right? And we talk about true, we mean, what actually happens versus engineering. So there's a graphic at the end that really shows how that's definition. So here we have true stress relating to engineering, we have true stress related to engineering using this equation here, where it's 1 plus strain, and then we can also relate true stress and strain, right? When we use K here, which is a strength coefficient, and this is using the logarithm. So if we plot the logarithm of the true stress and true strain, we can use an equation like this as well, where we're including the elastic moduli and the true stress and true strain. Right? So this equation here talks about true versus engineering strain as well. So it's the same thing, how we're relating true strain to engineering strain. I think the main point to make here is, in engineering, in this example is stress. It is, I guess, it's both stress and strain, but at the end, engineering is what actually happens. True is what we would want, in an ideal setting, but this is what actually happens with the true. So that's something that at the end, where definition occurs. So one thing we learned in statics was static beam forces, right? So like we talked about fixed builds. So where this is, we have to include both forces in the x and y direction as well as a moment. For rollers, you have to include a y direction force, and for a hinge, you got to include a x and y direction force. So this all translates to a normal statics problem where we have to set everything equals 0. So obviously, by definition, that is an equilibrium equation, right? So for all 6 and for the x, y, and z direction for forces and moments, we have to account for all of that to solve for any problem involving the beam or any other statics problem.
What we're talking about here is basically the idea that temperature change can also cause a stress of its own if it's constrained, as well as causing obviously its own temperature strain. So I think we're going a little out of order here because we're going to go in order of the columns, but basically I think it's this way. So basically, when you apply a temperature change, or there's a difference in the thermal expansion coefficient, you can cause a strain where the strain is given by alpha, which is the coefficient of thermal expansion, times the change in temperature. And it gives you a kind of thermal strain And combining this with the obviously mechanical strain, we can solve for stress. For example, in this constrained example, this directly leads to some kinds of stress. So it's constrained to expand in the x direction, while it's free to expand in the y direction. That's why we see that the sigma y, or the stress in the y direction, is 0, because it's able to still expand up and down. Meanwhile, you'll see that the sigma xx actually equals negative times the x modulus times the thermal strain here. I included a little algebra to show the work of how we specifically derive this.
So one thing that we can start with is work, right? That's a very physics one concept, and we can take that all the way to structural analysis with this example here, which is strain energy, right? So work equals force times displacement, right? But work done is also related to energy, and so if we look at potential, or if we look at kinetic energy, for example, you'll see that these equations are very similar, right? But they include both stress and strain, right? So we have volume of the object, stress and strain, and we're talking about a strain energy equation. We can also rewrite that, including force and change in length, right? So another way to write strain energy, and then it's not showing up. Oh, there it is.
Big graph.
So when we're talking about the modulus of resistance or resilience, it's underneath the linear part of a stress strain curve. When we're talking about all the way to fracture, when we're talking about that linear increase in stress and strain, that's when the modulus of resistance. Now, what is resistance? It's the ability for a material to either absorb or release energy, strain energy, when it is loaded or unloaded, right? So how quickly that's able to happen, and that is resilience, right? So that would be definition.
I think that's all we had for our presentation. Next up is going to be the derivation for C04. That's all.
Okay. Okay.
Can you just
So
drag that
if fun,
figure? Just drag
maybe before we go to that, if Fanendra has any inputs in addition to what I already mentioned.
No, sir, I don't have any specific inputs. Maybe, yeah, the columns which you have mentioned, they were here and there.
Yeah.
Maybe you can make it.
Yeah.
Do you have any recommendations for color coding or putting together things together in any sort of way?
Yeah.
Like other than just the colors in general.
I think there's a way to name the columns instead of the default values. So I think that will really help. And also, if you, as you said, have color coding for the different columns, that will also help. But I'm really impressed by the wide variety of concepts that you have brought out, including all the things that we have looked at in our course, as well as the previous courses, and some which you probably didn't even have courses for, but I think you've done a lot of literature review to see what exactly would come under this purview and how to bucket them. So I'm impressed with the wide variety, the spread, the diversity of the data that you have included in this. By data, I mean variables as well as equations, constants as well. But a little more care needs to be given to the bucketing aspect. So which comes under which category? I think it's a few of them are all over the place. So just make sure you give a lot of thought towards what comes under which particular category, because that is the main purpose of this whole exercise, to see that this bucketing can be done. First of all, classify things as either variable or constant or equation. And once you have done that, if it's an equation, it comes under one of the three categories. If it's a constant, it comes under, again, the equations, because those equations are going to be relating the variables. But if it's any of the variables, then it comes under those odd numbered columns, 1, 3, 5, and 7, where you have to be very, very careful about which particular kind of variable you're talking. So as long as you do that, I think you have a lot of information already in place, just that it has to be put in an appropriate way. And I think you can jazz up the sheet as well in terms of color coding and the headings. It'll look much better. And as I said, some places, if you can adjust the lengths of the columns to appropriately suit, and similarly the lengths of the heights of the rows to make sure that everything fits in appropriately.
So for this, we were trying to prove and derive that the C44 was equal to C22 minus C23 over 2.
Yeah. Just a minor point. Whenever you're talking of subscripts, it's better to talk of them in single digits rather than calling them as 23. You would call them as 2, 3. Okay, so just keep that in mind. And this is true for not just this course, but in general. So whether it is subscripts, or you're talking of, let's say, even anything which comes after a decimal place in a numerical value, for example, if it's 4.56, you should never say 4.56. Okay, so it doesn't make sense. So anything after the decimal, or which is a subscript or a superscript, you go by digit after digit.
So, like, the foundations of this is we start with the generalized Hooke's laws, like we talked about before. At the very, very top, when we start all this, we have this 6x6 matrix with C11 through C66. And so this is kind of the foundations for how we derive the rest of these equations. And then for the transverse values, we can assume isotropy in the plane that's perpendicular to the x3 direction. And so this allows us to simplify finding the shear modulus as well as the value of G23, E2, and then the Poisson's ratio in the 2-3 direction, which are the foundational units for what we use for the rest of these equations. And then for like the basic equation for an isotropic material, is that G is equal to E over 2 times divided 1 plus a Poisson's ratio. And so we specifically want to determine this for the G23. We're not changing the equation, we're just plugging in those particular values of G23 equals E2 over 2 times the value of 1 plus the Poisson's ratio 2,3. And so I did this kind of in the wrong order, where I just directly said this is equal to C22 over C23 minus over 2. But down here at the bottom, I explained why this is the case. And so for each of these, like, the definition of C22 is here, the definition of C23 is here. And so if you just do standard algebra, where we say what is C22 minus C23, we can find, once you combine all the, simplify the fraction, that C22 minus C23 is equal to E2 times the quantity 1 minus Poisson ratio 2,3 over 1 minus Poisson's ratio 2,3 squared. And so because of that, that is why then therefore we can say that G23 is equal to C22 minus C23 over 2. Now that only explains why G23 is equal to that, but based on that the stiffness matrix, we know that G23 corresponds to C44, and so therefore because those are corresponding values, we can say that the C44 is equal to C22 minus C23 over 2.
Okay. This is a valid derivation, but it's under the assumption that we already know G equal to E by 2 into 1 plus nu. My whole idea was to go back and look at, for isotropic materials, how that is derived in the first place. So not take it for granted. So that why is G equal to E by 2 into 1 plus nu? So then you start substituting for the or generalizing it for the anisotropic material. So I want you to look at the for isotropic, whatever you have written there, G equal to E by 2 into 1 plus nu. Look at that derivation and then substitute for all those quantities in the derivation with the ones using the appropriate subscripts that we have for the anisotropic or rather orthotropic material, which is also transversely isotropic. So then you will get, so this becomes kind of trivial if you just use G equal to E by 2 into 1 plus nu as a known equation.
Okay, that makes sense. I can just derive it from starting before that and derive why that.
Exactly. Yeah. So I do not want you to present that G equal to E by 2 into 1 plus nu, how it is derived, but in that place, use the same steps to derive your C23 equal to C22 minus, sorry, C44 is equal to C22 minus C23 by 2. That derivation has to come out of the same process which is used to derive G equal to E by 2 into 1 plus nu. Not take that as a starting point.
I can add that for tomorrow.
Okay. Sure. So great job overall. I'm really impressed by the amount of data, especially for the first problem, that is the take-home final that you presented. It's a really good mix of things. Just that the appropriate segregation has to be done, as I already discussed. So if you have any questions or doubts, you can ask Fanindra. Just spend some time with him. Also, if you still feel there's something you're not clear about where what goes and things like that, just send me an email or just ping me and I will get back to you as soon as I can.
So the variety is good, right? We have like a good amount.
Yeah, you have a good spread, so no issues with that. So more important that whatever you have already got in place, you put it in the appropriate columns and rows.
So you want us to present like, can we present like this as well, like on an Excel sheet, but just much nicer looking?
Yeah, sure. I was okay with the way of presenting. Just that we lose track once you start going down the sheet because you don't know what is
There's a
ABCD.
real,
Yeah.
Freeze the top.
yeah, that's just freezing the top column should be.
Yeah.
Top.
That's correct. Yeah.
So that small change
Yeah.
should make a massive difference.
Sounds good. And also, as I said, one more thing, if, just in case you have forgotten, the subscripts, the appropriate subscripts for all the variables that are used, like you have obviously copied and pasted from various sources. So over that, you can probably write what is the appropriate subscript so that you just don't just say gamma, you don't just say a sigma or a tau. You say like tau 1 theta, for example, in a particular place where it is because of torsion. So make sure that you are aware of which particular stress measure number or which particular strain measure number you're talking about. Same thing with the displacement and the forces also. Don't just say F or M. Talk about F1, F2, F3 or M1, M2, M3. Similarly, U1, U2, U3 and the rotations as phi1, phi2, phi3 to avoid confusion with theta, which we use for the independent variables r, theta, z, cylindrical coordinates.
Thank you.
Yeah, you're most welcome. I'm sure you have, if you have any questions right now, you can ask me. Otherwise, we can discuss offline.
I think you mentioned something where it was like you want the kinematics column to maybe be about geometric.
Yeah.
The geometry is relates to
Right.
kinematics.
So anything that you're talking about, geometric features like length, width, height, or radius, or a diameter, or different shapes that you're talking about, shapes and sizes, all these aspects come under kinematics. Because that, for example, you have defined all this polar moment of inertia or a torsional constant and things like that. All of that comes under the kinematics.
You wanted material properties to be under a constant law, is that correct?
Absolutely. And similarly, all the equilibrium equations like you brought in, I was really happy that you brought in things from non-structural aspects like the Bernoulli equation, etc., which is really nice because it's the same physics that we are dealing with, whether it's in fluid mechanics or solid mechanics. So it's good that you brought in that flavor as well. So all of those equilibrium equations will come under the equilibrium, the second column.
We'll just make it look much nicer and change where a couple things go.
Sure. Yeah. Sounds good. Yeah. So wish you all the best and I'll probably see you in person tomorrow. Take care. Bye-bye.
Yeah.
Fanindra, you had anything or you can probably discuss with me over WhatsApp or email if you have
Yes, sir.
any further feedback. Yeah. Thank you.
Yeah.
Bye-bye. Did everything go well yesterday in terms of the lab visits, the students?
Yeah,
Prashant went.
it was great. Yeah.
Okay,
Everybody's
okay.
really helpful.
Oh, great. That's nice.
We
Thanks.
have
Yeah, you said something?
we have a lab tour today too, right? Is that 2 p.m.?
That's correct. That's correct. Yeah. So Professor Jagdish will not be there himself, but he has allocated another of my colleagues, Professor Srisha Rao, and I've put his phone number, mobile number as well in the sheet that I shared with you. So you can just look it up. He will be waiting for you at 2:15 at the entrance to LHSR, which is the Laboratory for Hypersonics and Shock Research.
Like you can reach near the entrance of aerospace. One of my friends will be there.
Okay, so it's just we'll go to this like the actual.
Yeah.
Okay. Sounds good. Yeah. See you all. Bye. So try to reach there by 2 so that you have to walk from the main entrance of the department to the LHSR, which will be about a 5-minute walk. So because that person, the professor there will be waiting at 2:15.
Okay.
All right.
Okay.
All right.
See you. Bye-bye.